Welcome back to the classroom. My name is Mr. Wong. Today we're going to be covering Module 8 from the universe to the atom. We're going to be covering inquiry question number 3, the quantum mechanical nature of the atom, and we're going to investigate specifically the de Broglie matter waves, experiments related to this formula, and also the contributions of Schrödinger to the current model of the atom. Okay, the textbook references you'll need are these on the following. By the end of the lesson, hopefully you'll be able to gauge the difference between the contributions of de Broglie and Schrödinger. Depending on how long this video is, it might be split into 2 parts as well. Just to give you a bit of context of the atomic timeline, so we know that in about 400 BC, a guy named Democritus theorized the concept that atoms were the smallest form of matter. James Dalton actually demonstrated that in the early 1800s, followed by Thompson, who showed the charge to mass ratio of electrons and the existence of electrons. In 1905, Einstein came up with the idea of wave-particle duality. About 6 years later after that, Ernest Rutherford came up with the idea of the atomic structure of the nucleus with the positive protons, and we had Niels Bohr about 2 years later coming up with the concept that electrons traveled in quantized energy orbitals. What we're going to be looking at is a guy called de Broglie, and we've already talked about James Chadwick, so we're actually skipping back a couple of years. We know that James Chadwick discovered the neutron, so before then a guy named de Broglie came up with the concept that particles can also act like waves, which provides our explanation of the Bohr's model of the atom that we're going to look at. Okay, so don't forget these two were the people who came up with the concept of quantized energy. So Max Planck with his work with blackbody radiation, and Einstein with his work in the photoelectric effect. Just before we begin, just to kind of give you a little explanation, remember diffraction is when waves travel through different obstacles, travel around different obstacles, and interference is when we have constructive or destructive interference. Interference is where light constructs constructively or destructively, forming dark and bright bands. Just want you to have a look at this image here. We know that the interference pattern of a wave gives you blurry lines here. Now, this is actually using a electron microscope or electron thing, so that actually shows you there are some really blurry shadows here. What we can imply from these blurry shadows is there is some interference pattern. Now, if we're using electrons to help us show these images, electrons being particles, there are implications that this electron could have wave-like properties and not just particle properties. As a matter of fact, you can actually diffract electrons, so you can see in these diagrams here. Now we know X-rays and light are both electromagnetic radiation, so they're waves, so of course it's predicted that they will have diffraction patterns. However, with electrons, as you can see here, they also have diffraction as well. So that would imply that electrons do have wave-like properties. Okay, and this is where we apply this concept to the Niels Bohr's model of the atom. So if the electron did have particle wave duality, what is the implications to the Bohr's model of the atom? And that's what we talk about a guy called Louis de Broglie and his concept of matter waves. Okay, so you can actually see this here already. You can sort of see this standing wave forming as this electron is orbiting. That's what we're going to be talking about. So he came up with the idea that all particles have a wave-like nature, as well as its own particle nature. The idea is very simple. If we talk about quantized energy states of the electron shells, we can think of it as whole number integers. Okay, so whilst the charge, so we know that things like the charge of an electron and the energy of a photon of a specific wavelength are discrete. We also know that interference patterns formed by waves, like standing waves, come in specific integers. Okay, if you want to remember this, you can think about the standing waves you create in harmonics and overtones when it comes to music. So what implication can this have? Now, think about it this way. De Broglie basically explained the stability of an electron orbit is due to the fact that these orbits are standing waves. So the electron itself is orbiting the circumference. However, this movement is essentially a standing wave. This standing wave means that the charge isn't actually moving. Okay, there is no propagation of charged particles. It's forming a standing wave, hence why there's a really stable orbit. Hence, no electromagnetic radiation is formed. Okay, so let's think about it this way. Let's think about if we look at the basic wavelength of an electron and imagine that electrons actually do produce standing waves in its orbit. What we can imagine here is the reason why electrons don't emit electromagnetic radiation in the orbit is because it's not orbiting the nucleus, it's just undergoing this sort of constructive interference, producing these standing waves. Okay, so if you can imagine each individual electron shell as a standing wave, then this is each electron shell has undergone constructive interference. Okay, so as we understand, standing waves come in specific integers. Every successive energy level we go up by is the same thing as saying I'm increasing the integer or the wavelength of each shell. So if I have in shell number 3, I have 1, 2, 3 wavelengths. If I go to shell number 4, I'll have 1, 2, 3, 4 wavelengths. And this is how we establish the idea of the discrete quantized energy levels. Because we know that discrete energy levels come in a specific integer as well. And so that applies very nicely if we're talking about if this was a standing wave. So everything fits really nicely together. So what we have here is a slight difference between the energy levels and gaps. So where we have constructive interference, okay, where we have constructive interference, we are seeing the energy levels. So this is the specific energy level that the electron can belong to. Now any kind of gap, so let's say we have N1 here and then we have N2 here. Now the reason why there is all this empty space is because in that empty space there was some form of destructive interference, and so there is no energy level in existence. So there's no energy level. As a matter of fact, this is the energy gap that's separating the energy levels of the electrons. Okay, so that's how you kind of explain these orbitals that Bohr has proposed. So that's our energy gaps that we were talking about. Alright, so let's kind of summarize what de Broglie's explanation has kind of given to the Bohr atom. So as electrons don't orbit the nucleus because they exist as standing waves, that explains why there is no emission of electromagnetic radiation. This is consistent with Bohr's postulate that the circular orbit is stable. The reason why it's stable is because the electrons are stationary standing waves. They're not actually moving around the orbit of the nucleus. We also know that the standing waves only form if there is some constructive interference. Now what's actually happening is the electron moves so fast that it essentially forms its own constructive interference with itself, you could imagine. And so the same integer of the wavelength is increased for every successive level. Okay, so if the wavelength was 1 for the first shell, so if the wavelength was 1 meter, let's assume for the first shell, then the second shell will be 2 meters, because it's the common factor is 1 meter here. The energy gaps between the orbits are caused by destructive interference. So any wavelength that we form that's not part of the integer of 1, for example, let's say we have a wavelength of 1.5, then that can't be any particular energy shell that we have there. So any non-integers of the original wavelength, fundamental wavelength you could say, then no electrons will exist in that gap. Okay, so what does that have? What's the impact of de Broglie's proposal? Now, if particles are waves or have wave-like properties, then that implies that, you know, they must have a wavelength. And if it has a particle, if it's a particle, it has to have momentum. So you can find the wavelength and the momentum of the particle. We call it matter waves because obviously it's the wavelengths of particles, things with mass. The importance that it provided was the credibility of Bohr's atom. So it explains why electron orbits were stable and we don't emit, or they don't emit, electromagnetic radiation. And it also helps us find the wavelength of the electron, which previously wasn't known. And it also explains why electrons don't accelerate into the nucleus because of that. Okay, because if it's acting like a wave, it's not acting like a particle in that stage there. So let's actually come up with the derivations to work out his formula here. And it comes up with a really ingenious idea because it's using the derivations of the E equals mc squared, so special relativity, and it's using Planck's equation as well. Okay, so this is the formula we've dealt with. What we can see here is the energy of a wave, and we have the energy of the particle. So mc squared, that comes from the special relativity formula. So from Einstein's special relativity, and we also get Planck's equation. Okay, and so we get mc squared here. Now what we have here is, I just want to move this one of the c's over to the other side. So it's the same working out here, but I'll explain it as we go. So if I move one of the c's over, so it would be hf over c. This c, remember, is velocity, right? So I can just rewrite it as mv. Now we know that momentum is mass times velocity, which means that the particle we're looking at, okay, this momentum of this particle will have such and such that. So that's what we have, which also means that I can also find the wavelength of this particle. Okay, so we know that from the equation, velocity equals frequency times wavelength, that the wavelength is essentially velocity, let's see, velocity over frequency. So we have the inverse, this bit here is 1 over wavelength that we're finding here. So the momentum of a particle is given by Planck's constant times the inverse of the wavelength of the particle, which gives us this value here. Okay, this value here. If I want to rearrange to make the wavelength the subject of the equation, I will get wavelength equals to Planck's constant divided by the mass of the object times the velocity that it's moving at. So the implication that this has is twofold. It actually tells us that any mass object will have a wavelength. So particles will have a wavelength. So particles have a wavelength, but it also means that any waves should technically have some form of mass to it as well. Okay, so this is a really important equation. It kind of shows that particles can be waves, and waves, obviously what we already knew by that time, could behave like particles there. Okay, so the reason why this equation is really important, if we implement it into Bohr's third postulate, Bohr's formula, or Bohr's third postulate about angular momentum, was that there was this formula here. So nh divided by 2 pi was the angular momentum of the electron in circular orbits. Now what we do know is, if we go back to this equation up here, the angular momentum of any object is 2 pi r, so the radius r here being the radius of the electron's orbit, okay, and obviously n wavelength is the overall, wavelength circumference you can think of. So wavelength of the shell, so the energy shell, it can also be seen as the circumference in which the electron needs to orbit the energy shell as well. Okay, now we know that from de Broglie's equation, lambda is equal to h divided by mv. So if we just substitute that into the equation, this is the number we get. Now we want to rearrange it where it's nh divided by 2 pi. So what we can find here is, if we move mv over to the left hand side, we'll get this equation here. And then if we move the 2 pi over, this is the formula, the angular momentum of the particle, so the angular momentum of the electron. And we can also find this, the angular of the momentum of the wave as well here. So that mathematically demonstrates how we can derive the angular momentum of Bohr's third postulate, and again, therefore, justifying its existence, justifying or validating Bohr's third postulate there. Okay, so this is the equation we have here. Now h is obviously Planck's constant. The mass we're dealing with is whichever object you want to look at, and then v is the velocity of the object, and then obviously lambda is the wavelength we're looking at. Okay, so let's try this question and look at how de Broglie's equation can show us the velocity, the wavelength of the electron, and what does that mean in general. So the wavelength of an electron is h over mv. So we know that Planck's constant in your data sheet, and we know the mass of the electron. So 9, that's given to you in our question here, times the velocity in which the electron is moving. That's the wavelength we're dealing with here. That gives us a wavelength of 3. Let's see, what do we have? 3.23 10 to the power of minus 10 meters. Next we want is the velocity of an electron if its quantum wavelength is this value here. So we want to make v the subject of the equation, so everything's just rearranged where mass times lambda. So same idea here, minus 34, mass of electron times the wavelength. So that's given to you there. That should be a minus value. Okay, so that's the velocity we have there. Use the wave equation to find the quantum frequency of the electron. So we're using just velocity, frequency, wavelength there, and then obviously calculate the energy, so we use Planck's equation here like so. Okay, so it's not an overly difficult question to complete, just a little bit of rearranging involved to show how everything kind of matches up together. Okay, so these are the values that you get here. Just remember this value is -9, and so that's what we get here, just the rearrangements required. Okay, so what is the importance of all this? Well, just before we get into that, a really funny idea, a really funny thing is de Broglie's proposal came from the diffraction and interference of electrons, which gave the implication that it had wave-particle duality. At the point where he actually made this theory, there were no real experiments that actually showed for what he did at the time. So what we need to know now is who actually demonstrated the diffraction patterns of the electrons, and then how did they actually do it. And that's going to be the third part of this dot point, which is the experimental evidence that demonstrates the matter waves principle. And that comes from two duos called Davison and Gemma. Okay, they came up with a really simple, or I wouldn't call it simple, I'll rephrase that. So they came up with the idea where they used cathode ray tubes. As you know, cathode ray tubes emit electrons. They fire it through a crystal that will diffract the electrons. Okay, so that's the idea there. So you have an incident beam, that being the electrons, and fires through, and it creates this diffraction pattern here. Now the setup is quite simple. You have sort of a electron, so you have your cathode and your anode. The anode obviously accelerating through the electrons, so making the electrons accelerate through, making it go faster. Now the thing about this experiment was there was a little issue in the setup. So there was a little crack in the vacuum tube that allowed the air to oxidize the nickel that was inside the vacuum tube. Now to remove the oxide layer, the material was actually heated up close to melting point, and by heating it up to melting point, once it started cooling down, this actually caused the nickel to form crystals, where the regions where you can imagine what we mean by crystals is where it forms sort of a lattice system. So it kind of lines up into this sort of lattice system here. Now the reason why this is so important in the actual investigation was this crystal lattice had a smaller gap, so the width was smaller than what the electrons could provide. And remember, the whole concept of diffraction is waves bending around an obstacle. So with this smaller gap, the electrons couldn't just go straight through it. It would have to bend around it if it was indeed behaving like waves, which we did actually see. So what they found was these electrons were reflected off the surface, having these diffraction patterns and causing an interference pattern similar to an X-ray. Okay, so this was the pattern that we see here. So once it goes through the actual crystal now, it's actually being bent into different directions, different angles, and that's why we see this diffraction pattern, this interference of the electron there. And so this experiment establishes that electrons do behave like waves because it can be diffracted, it can have interference patterns. And they found that the overall wavelength was similar to the predictions made by de Broglie. Okay. Another person that also investigated electron diffraction was J.P. Thompson. Now, J.P. Thompson is actually the son, or he is actually the son of J.J. Thompson, and he managed to conduct an experiment where he fired electrons and penetrated through metal foil, producing diffraction patterns of its own. So there's actually two people who demonstrated electrons can be diffracted. J.P. Thompson using aluminium foil, while as Davison and Gemma used the nickel crystals that were formed after their vacuum tube had actually cracked. So there's that. Now the actual overall impact of de Broglie's proposal is very significant. If you actually have a look at the different ways we see things, so our eyes has a specific range that we can, observe particular objects. Now, obviously, if we can't see them, we tend to use microscopes. These microscopes are generally what we call light microscopes. So we use interference diffractions of light to magnify the image of really, really tiny objects. But there is a specific range that even light can't really show us. Okay, and so it's from like 100 nanometers smaller. We have the use of electron microscope. Now we know that the electron has a much smaller wavelength than light, and so the smaller the wavelength of whatever we're trying to use, the better we can actually see even smaller objects. Because if the wavelength isn't smaller than the object itself, we won't be able to detect it and see it. So things like viruses, DNA, glucose, the structure of the atom, we actually use X-rays, and we also use electron microscopes to actually look at these here as well. So without the work of de Broglie, we wouldn't have electron microscopes. We wouldn't be able to look at the different structures of viruses, DNAs, glucose, and atoms. So that's really important. Okay, so that kind of summarizes what de Broglie did, and as you can see, the video has gone on for a fair distance of time. So the concept we're going to talk about with Schrödinger is going to be published in a separate video, so you can look at the links that takes you there. But just remember what de Broglie actually said, that particles can behave like waves. The wavelength we talk about is this equation here. We call it matter waves, so the wavelength of particles. We also know that using this equation, we can mathematically derive the stability of electron orbits, the angular momentum, this equation here. The reason why this was proven to be true was the work of Davison and Gemma, and also J.P. Thompson, because they could actively observe the diffraction of electrons, confirming that particles do act like waves. Okay? So with that, that concludes this part of the video. Thank you for joining with me, and you can always forward on and look at the contribution of Edwin Schrödinger.